She's eating. Okay. Okay. So we're so glad to have Noga Alon here with us today. He's a professor of math at Princeton and also professor of Emeritus here at Tel. He's very decorated, won the Israel Prize, the Wolf Prize, and we're so happy that you're speaking here today.
Thank you. And so, you know, last week I learned that the number of people who want to hear what I have to say about AI much larger than the number of people who want to hear what I have to say about something I do understand. But that's okay. So it's always a pleasure to speak here. Thanks for the invitation, and thank you all for coming. And I'll talk about this distance ordering and sign patterns. And maybe one of the main reasons I want to speak about this is because I want to tell you about some proof technique that I think is useful. So that refers to the word sign patterns here. And in fact, the basic variant of it found some interesting applications in discrete mathematics, in theoretical computer science, some years already. And I'll try to mention some of the quick early applications. And now we have some variant of it that I think should also be useful, so I want to tell you about it. And all the new results are joint work with Colin Defant, who is now in Harvard, Noah Kravitz, now in Oxford, and Daniel Zhu in Princeton. So let me first by telling you about the problem I want to address now today. And this is order points by sum of distances. So it's very simple to state. We have a fixed set C of points in the D-dimensional space. And you can think even about D equals 2. So it's equally interesting in the plane already. So these are a set of points, n of them. And then we have, I'll soon say what I mean by this word generic, another set V of vantage points. And there are k of them. And then we want to order the points of C according, the points of C according to the sum of distances they have from the points of V. Right? So for each point of V, I take the sum of all its distances, or the average, to be the same, and then I order, let's say, from small to large. And what I meant by generic is that we just don't want to bother about cases of equality. So let's say that we never have equality with two such sums of distances, and we order them. And we can look at the set of all orders that we get like this, F, K, T, and C. And we count how many of them we have, and we want to know how large this can be. So this is what I denoted here by F, K, D, N. This will be the maximum possible number of orders that we can get on a fixed set of n points in Rd according to the sum of distances from k points, and you are allowed to vary the k point. Now I write only one sentence of this board, so don't bother moving, but because I keep talking about this function, so I want that it would stay here, and let me see if I can. So this is just trying to be the maximum possible number of orders of ordering of a fixed sum set C in the D-dimensional space. This is of size n, and we order them by a sum or average of distances from k. Okay, this is this what I write, and maybe write one other formula close to the end, but we have enough place. Okay, so I want to understand this, and let me tell you something about motivation for that, which I'm not sure is very convincing, but that appeared in the early papers on the subject, and this is so it's a possible interpretation. We have this C here, we can think about it as a set of candidates. Okay, and each candidate has an opinion on D issues. So maybe the X coordinate can be foreign policy if you are left wing or right wing. The second is what is your opinion about who should serve in the army and who should get child support and things like that. And therefore, each possible candidate is just a point in RD. And each possible voter or vantage point is also a point according to her or his opinions. And it makes sense to think that people like the ones who are close to them. So we order by average distance or sum of distances. This is one reason, and we want to understand this function.
Okay, what's asymptotic here? N.
Yeah, so here usually N will be large, although at the end I'll mention something about the other. So mostly I think about fixed D and K, and the large N. You can say that the voters, usually you're supposed to have more voters than candidates. Well, maybe it's a committee, right? So the voters are committee members, and the N are the candidates. So this is so mostly N will tend to achieve this. Okay, so here is some early results about the case of K equals 1. We just ordered the point by their distance from one given point. That's very easy to understand and to solve completely exactly. So what we do, you see here that we have these three, in this case, black points. These are the candidates, the point C. And if K is 1, then what we can do is that for each point, we can take the line segment connecting the pair. And then we take the bisecting hyperplane. In this case, we are dimension 2, so it's a bisecting line. And the bisecting hyperplane tells you with respect to, for example, if you look at this one, it tells you with respect to these points, on the left side of this line, this one is closer to any point that lies on the left side. And on the right side, this is closer. So if I take all the N choose 2 bisecting hyperplanes, I have this hyperplane arrangement. It will split the space into connected components, and each connected component we just have this determines exactly the order, right? So here, like if the point is here, then you get a different order, and here, and here, and here, and so we kind of understand how it looks, and this will be the animation that you will see here. So you can view it as a proof that I'm not using any AI to prepare my slides. Okay, now there are formulas for the number of states or the components of a hyperplane arrangement. This one is N choose 2 hyperplanes in RD. Well, they are not quite in general position because they are, but you can take this into account also, and you get an exact formula. But anyway, in case of asymptotic, so N large and K and D fixed, this behaves like N raised to the power 2D. So basically, N square or N choose 2 hyperplanes in dimension D is basically the number of hyperplanes choose the dimension. Right? And to Okay, but already when k equals 2, so you take the sum of distances from 2 points, then it gets much more complicated to understand what's going on. And in particular, there was this question suggested in a recent paper 5 years ago by Carbonero et al. And they asked to estimate this f of 2, 2, and n. So we have 2 points, and we order according to the sum of distances from this pair of points. We have n fixed points in the plane, the dimension is 2, and we want to know how many orders we can have if we let the 2 points vary. And specifically, they asked if it's exponential in n. So they did have an exponential upper bound. Since the total number of orders is a little bit more than exponential, it's factorial, so exponential in n log n, and they knew that it's not more than exponential, and the question was, is it really exponential? And the answer turns out to be no. So this special case of what we proved with calling Defant, Noga, Kravitz, and Zhu, is that, again, fix endpoints in the plane, and you look at the sum of distances from 2 other points, how many different orders you can get. So this we have like n to the 8. In this special case of a more general result, that for every fixed k, well, in dimension 1, there is something special, and so worry about it. In dimension 1, it's pretty easy to understand what is happening. But if the dimension is at least 2, and the number of vantage points or voters is k, then as n grows, the number of possible orders, we have like n to the 2dk. So if d is 2 and k is 2, this is 8 that we get here. And I want to mostly almost show you the upper bound. I should say that really, technically, the lower bound is in fact more complicated, but maybe less interesting. So I don't think that it is likely to lead to other things. And the upper bound, as I said, I think is an interesting technique that is useful to know. So
dependence on the nk is exponential. Dependence on the nk.
The dependence on d, it's exponential. On k, at least it's not polynomial, because I mentioned at the end that for some k we get all.
And the lower bound of some explicit construction or probabilistic?
No, it's probabilistic, right? But it's kind of a combination. But basically, but I don't know. Okay, so let me talk a little bit about sign pattern. Yeah,
so before you did it, they didn't know that it's polynomial? Before you did it?
So they didn't know that it's polynomial. It was not known it's polynomial. I don't think so many people thought about it, but it was not known. So any other questions about this before I start to talk about sign pattern? Okay, well, let me talk about sign pattern, and this is more general, so you can for a while forget what I said so far. So here is the relevant description of what we mean by sign pattern. We have a sequence of m functions. So it's a moment just a collection of functions. I don't want to assume anything about them afterward. Maybe I assume something. And these are all real functions of n real variables. So each function fi takes an n-tuple of any number and times together a real number. And then we take a point x for which no fi vanishes, although we can allow it to vanish also, but let me simpler to do it this way. So no fi is 0, and then we can define the sign pattern of this sequence of functions at the point x. So we just plug x there, and we look at the sign of each function, either positive or negative. These are real functions. So we get a vector of length m of plus minus 1s, depending on positive and negative. And the number of time patterns is just the number of distinct vectors that we can get as x varies over all the points in which no fi vanishes. So this is in general a number between 1 and 2 to the n. And of course, if we don't assume anything about the functions fi, it can be anything between 1 and 2 to the n. But the hope is that if we know something about them, then we can say something intelligent about this number. And here are two all the results of work in real geometric geometry. So this extends earlier results of Milnor and of Tom. And it says that when the functions are polynomials, then we can have pretty good bounds. So these bounds are in some sense pretty close to being tight. And it says the following: so if each fi is a polynomial, it's a polynomial in n variables, and let's say the degree of each polynomial is at most delta. There are some versions with different degrees, but let's not worry about it. And the number of polynomials is at least the number of variables. Then the total number of sign patterns is what you see here. So basically, you take the sum of the degrees of all polynomials. You multiply it by some constant vector, 4e, I wrote here, divide by the number of variables, and raise to the number of variables. Now, actually, the exact bound has a more precise expression with some binomial coefficients, but I wrote asymptotics, which is the one that will be interesting for me. Right, so you see, for example, that if n is 1, then this would be linear, the total degree, and you can convince yourself. So if n is 1, it's very easy. This is the case. Now, the way this is proved is actually by what he really proves is the following. So he bounds a number of connected components of green semi-variety. So we have this function, f1 up to fm, each of them is a polynomial in n real variables of degree at most delta, m is fixed n, and we look at the connected components of all the set of all points in which no fi vanishes. So this we kind of throw out all the places where some fi vanishes, and this has some number of connected components. And the number of connected components is bounded by that expression for e delta m over n raised to the power n. And you see this obviously implies the other thing, because if we are in the same connected component, in the component no fi can change sign because it's a continuous function. So if it is positive and negative, then by the intermediate value theorem, it will be zero sum inside the component, but inside the components it's not zero. And again, as a sanity check, you can see that if n is 1, let's look at this decade. So with n equals 1, connected components are basically the number of zeros, right? Well, plus 1, maybe. So we say that if we have polynomials altogether, they don't have too many zeros. Well, they don't have more zeros than the sum of the degrees. So this is what we get here. We don't need the 4e for n equals mass, but it's okay. Good. So I want
this follows from VC dimension something.
that what?
It's equivalent to bounding a VC dimension.
No, so I mentioned VC dimension soon. It's this is a special case of Warren. So it's without the geometry. He bounds all the Betti numbers. So we care only about the zero Betti number, which is the number of connected components, but he bounds some other things. It's true that we can use this thing to bound the VC dimension of things. There are some papers that do it, but I not mention it. Well,
okay.
I guess I mentioned.
But the example you gave in the very beginning, the k equals 1, wasn't it almost exactly like
Yeah, so k equals 1 also we can get it from this because it's polynomials. And yeah, you can say that. So it's related. I'm going to mention 3 dimensions soon. But feel free to make comments and ask questions. Okay, so I want to mention, as I said, some quick early applications of this sign pattern method before I tell you about some variety of it, which is more general. And one thing I wanted to mention is the connection between sign rank of a matrix and sign patterns. So what is a sign rank of a matrix? We have a matrix of signs. So it's a matrix of plus and minus ones, not necessarily a square matrix. And the sign rank of it is that wherever we see plus, we are allowed to write a positive number. Wherever we see minus, we are allowed to write negative number, and we try to make the rank of the matrix as small as possible. So this is a sign rank. And here is an example. So you see this matrix. It looks like some version of the identity matrix. It has minus ones in the diagonal, plus ones everywhere else. And I claim the sign rank here is 3. And actually it's 3 in this example, even if this would have been an n by n matrix with negatives on the diagonal and positive everywhere else. But let me show this example. So you see, to show that it's at most 3, we can write these negative numbers in the diagonal. We don't have to write the same everywhere, but in this example, this is what I did. And we do these positive numbers everywhere else. And now you see that the sum in every row is 0. So the codimension is at least 1. So the dimension is at most 3. And you can show that the dimension is also at least 3. And as I said, even if this would have been n by n matrix with negatives on the diagonals and positive everywhere else, then it's still, no, C3.
No, but you write n minus 1 the diagonal.
No. You do something more complicated. If you write,
you need different numbers then?
Yeah, if you write n minus 1, then the rest
Just
will be
everyone
n
minus one.
Right, yeah. So you have to think about it, but it's too difficult. And a geometric interpretation of this is it's a sign rank of a matrix is a minimum dimension D, so that in RD you can assign a hyperplane HI for every row I and a point PJ for every column J. And what you want is that the jth point lies in the positive side of the ith hyperplane, even only if Aij is positive. And this is just because a matrix has rank D, even only if, let's say, n by n matrix, even only if you can write it as an n by d matrix times a d by n matrix. And then the rows of the first matrix will be the coefficients of the hyperplane. The columns of the second would be the coefficients of the point. So this is equivalent. And here I show examples that you see this is a sign rank of this is 2, and here are the hyperplane, and here are the points, and you see that, for example, H2 corresponds to this row, and you see, so with respect to this hyperplane, a line in this case, then only P1 is on one side of it, and P2, P3, and P4 are on the other side, and this is what we see in this line. Okay. Now, there was some reason to look at this sign rank. It appears in several things, but an early motivation came from a paper of Bathory and Simon, and they showed the sign rank of plus minus 1 matrix determines what is called the unbounded error communication complexity of the function given by A. So what do we mean by this? We have this matrix of signs that is known to 2 players, Bob and Alice. And then Alice knows the row I, Bob knows the column J, and then they have to, as we usually do in communication complexities, they send bits to each other. They try to minimize the number of bits. And at the end, H, let's say, has to just guess the value of Aij, and it just has to be right, which probability bigger than half. We don't care about how much, so it can be half plus 1 over 2 to the 8. So just a little bit more than half. So it's a very powerful model because we don't demand much. And it turns out it's the minimum here of the number of bits that they have to send is basically log base 2 of sign rank of A, maybe plus 1 or C, 4, whatever. So if the sign rank is very small, like in this identity matrix, the communication complexity is like 2 or something. It's really very powerful model. And maybe, okay, so I have here, of course, a compulsory picture of
Alice and Bob.
Of Alice and Bob. And you know that actually, I once saw a lecture given by Ron Rivers. And you know, before the beginning, so someone presented him, so first he's one of the inventors of the RSA crypto system, did this, he did that, so on. And you could see that Ron was not particularly happy. And then he started the lecture and he said, you forgot to mention my most important contribution, and that's the invention of Bob and Alice. And it turned out that Bob and Alice indeed appear first in the original paper on the RSA crypto system. And you know, so the idea was to get two parties with the initials A and B, and indeed this is being used from then on. So this is what Ron reversed with use as one of his most important contributions. Now I also wrote here that the sign rank is related to a linear classifier in learning theory, so that's the earliest example of a problem or an algorithm for a problem in learning is a perceptron algorithm by Rosenblatt in the late 50s, and trying to apply it for other things, we kind of correspond to embedding a general matrix. These those who want to learn, let's say in the PAC model as points in hyperplanes. But this is not okay. So this question of Patu and Simon, I mean, their motivation led them to ask what is the maximum possible D sign rank of an n by n matrix, right? Because this tells you what is maximum possible unbounded error communication complexity. Okay? You see the communication complexity of every n by n matrix is not more than log n, because Alice can send log n bits describing its row, and then Bob will know exactly which probability 1. And here somehow, because as I said, this model is pretty powerful, it's hard to find any explicit function for which the sign rank is big, for which you need to send many bits. But it can be proved, and I'll show you all about that. So this is a very old result with Peter Frankel and Boyta-Redel, that it is at least linear, so at least n over 20, which means that the unbounded error communication complexity will be log n minus 4, maybe minus 5. And so at most n over 2, roughly. So always you can make it somewhat small for any matrix of plus minus 1. And I want to show you the lower bound because it really follows in a few lines from this Warren theorem. You just count it. You see the signs of the entries of any n by n matrix A of rank at most D are just the signs of n squared quadratic polynomial. So you write it as a product of an n by d times a d by n. You have 2dn real variables. Each inner product is a quadratic polynomial, and therefore you have n squared quadratic polynomials in 2dn real variables, and we have the bound for the number of those, right? So the bound that we get from Warren theorem is this 4e times 2 times n squared. So this is what is written here, divided by the number of variables raised to the power of the number of variables. And this has to be at least the total number of n by n sign matrices if every n by n sign matrix is sign of D. You just solve it. So this would give some linear row about 14. And there is no explicit example. So this the counting argument shows that most functions do require most sign matrices do require a linear sign rank, but to get explicit example is let me say a related thing because it's also a very quick application. So that was a question of Scheiden a bit without the one Simon. And they asked, what is the maximum possible sign rank of an n by n matrix of signs with DC dimension 2? So we want now not to allow any matrix, but we want matrices that are simple subsets. And DC dimension 2 is essentially the simplest because VC dimension 1 is somehow 2 simple. Okay, and so I wrote here, but let's go over it quickly. Probably many of you know the definition of a VC dimension and how to not. So the VC dimension of a matrix of signs is the maximum cardinality of a set of columns, so that if you look at the projection on this set of columns, you get there all the possible signs. So here in this example, the VC dimension is at least 2 because you see that on these two columns, the first and the third, you get all 4 possibilities of plus, minus, plus, plus, minus, minus, and minus, plus. And of course, it cannot be 3 because for 3 we would need 8 rows, but we have here only 5. So the VC dimension here is 2, and somehow if matrices have small VC dimensions, they are simple. So the VC dimension, so I wrote here that for VC dimension 1, the answer is 3, and this, but we will be interested in a bigger VC dimension. And here is something that we proved some 10 years ago with Shaimuran and Amir Yudayov, is that the maximum possible sign rank of an n by n matrix of VC dimension 2 is up to logarithmic terms square root n. That is both upper and lower bound. And again, the proof of the lower bound is almost the same as the one that I showed before. We just need to get many matrices of VC dimension 2 for the counting argument. And they come from a specific graph of matrix, which is the incidence graph of the points and lines of the projective plane. But just say that this is a specific matrix, n by n sign matrix, which has about n to the 3/2 entries, which are plus, and all the others are minus, and it does not have a 2 by 2 submatrix of pluses. And therefore, if you think about it, if you look at any matrix obtained from it by changing pluses to minuses in any way you want, it will still not contain a 2 by 2 submatrix of 1s, and therefore the VC dimension of it cannot be 3. So you can easily convince yourself that if the VC dimension is 3, you do need a submatrix of 2 by 2 of pluses, and therefore this would give us many matrices of VC dimension 2, right? 2 to the n to the 3/2. And then we just write the same inequality as before, and we solve it, and we get this lower bound. So again, it's very short and very simple. And see, both these proofs, I don't know to prove the lower bound without some real algebraic geometry. So it seems that you need, it's very simple to answer without this, but it seems essential. Okay, let me go back to our order. So we wanted to prove that this f of kdn, the total number of orders of a fixed set of endpoints in Rd according to the sum of distances from k points, is not more than n to 2 decay. And so this is what we have to show. Right? So we fix a set of endpoints in Hardy, and we look at the order. Now, this is it's written here. So you can look at the collection, just what we did at the beginning for K+1. You can look at all the n choose 2 functions of the form. So for every 2 distinct points of C, right, we fix a set. So these are fixed already. For every 2 fixed points C, you can look at the sum of distances from the K point of C, sum of distances of C from these K points, minus the sum of distances of C prime of these K points. And if I would know the sign of each of these differences, then I would know the order, right? Because for every pair, I would. So, and again, I want to stress here that the points C prime are fixed because we fix a set. So the variables here are just d times k coordinates of the points vi. Just have, so we have n choose 2 functions, and we have d times k there. Now, and what I said is that the sign of them determines the order. So if we would have ordered by sums of squares of distances instead of sum of squares, then everything would be fine. This would be polynomials. Right? Squares of Euclidean distances are polynomials. It would be quadratic polynomials. In fact, it would even be linear polynomials because you can write down the differences. You see that the quadratic terms cancel each other. And then we would be able to substitute, say, in Warren, and we would get, and it would actually give us the correct bound. Because we have this n choose 2 polynomials, they would be, say, quadratic, and we have this divided by, so the number of variables is dk, so basically it's n to the 2 dk, which is what we want. But the trouble is that the functions here are not polynomials, they are radicals, right? So they are sums of square roots of quadratic polynomials. And in fact, you can show that for such functions, the number of sign patterns may be much larger. In some sense, we cannot really bound it if we don't know anything else. And I wrote here some example that you don't really have to read too carefully. So we can take one small number data and we can write this. So functions here are motivated by the fact that the derivative of the function square root x is very large when x is close to 0 and is not large when x is not close to 0. And because of this, if you have a sum of differences of square roots that looks like this, you see that when you substitute here x equals I, this is delta, right? The square root of delta square, and this is 0. So this is delta. And for each of the other i's, this would be much smaller, it would be close to delta square. You can complete yourself just writing that or using the mean value theorem. So that means that if you have an expression like this, then the sign of this function at the point j is really determined by aj. It doesn't care about all the others. And this means, so you have to play with it, but it's simple. This means that you cannot get anything. So even if we have one variable, we can write down such m functions, and we would, so still each of them will be just a linear combination of square roots of quadratic polynomials, and we would get all the 2 to the n possible sign pattern. So there would be no bound whatsoever. The only thing is that saves us here is that the number of square roots that we would have to be very big for this. It would have to be like 2 to the n. So we could still hope, I wrote it here, I think, that in our case, each function is a sum of small number of square roots. And the hope is that if each function is a radical, so it's some linear combination of square roots of quadratic polynomials, but of a small number of square roots, and you have a good bound. And indeed, this is what we proved in this paper with colleagues Kravitz and Zhu, and I'll show you the proof is by a very simple reduction to Warren theorem. But this is time patterns of sums of radicals, that if we have a collection of m real functions fi, each of them is a linear combination of s roots, in our case s is 2, of let's say positive polynomials of degree at most delta, then the number of sign patterns, we get the same expression as before, only we have here an extra term of s raised to the power r minus 2. So s in our case will be 2, r will be small in our case, right? So this will be, I mean, the dependence here on s and r, which is probably not tight, is pretty bad, but for our case, it would be good enough. So let me say something about how this is proved, because it's really simple, although it was quite a long time to realize this is what we have to do. So you want again to bound the number of connected components of the set over points in which none of the function is zero. So the trick is to multiply, as I said, I wanted to write one more thing. So the basic trick is this. Know that a minus b times a plus b. Right. So this is a squared minus b squared, which means that if a and b were square roots, then after I multiply it by this, then I get polynomial, right? Okay. And this has an extension, which is called the conjugate trick in Galois theory, that if you have some linear combination of such radicals, let's say square roots, and if you multiply by all the conjugates, so there are many of them, but then you will get actually a polynomial. So the trick is, so we have this semi picture. So we have these things that we want to bound the number of connected components, right? And what we do is that we multiply it by additional things. So it looks like these additional things. This can only increase the number of connected components. You have to make sure that nothing gets identical to 0, but this can be done. So if after the increase it is still small, then this is the upper bound. And basically this is what is being done here. And let me just sum that in our case. So if we do it and we plug in this formula for the case of radicals, then the number of variables will be dk, the number of functions n choose 2. Each of them is a linear combination of 2k square roots of polynomials of degree 2. So you plug it in everything here, and what you get is this n to 2dk because this r is small. So basically, that's it, and this is the extension we want to mention. Let me just use the last 3-4 minutes to tell you some open problems which are related to the disease. So the first one is about this old thing, and maybe the motivation for communication complexity is not strong, but still, I think it's a very natural question. Is what is the maximum possible sign range of an n by n matrix of signs? So I told you that an upper bound is roughly n over 2, a lower bound is maybe n over 20, you can optimize, so maybe it will be better than n over 20, but there is a gap. It looks like the truth should be close to n over 2. This is the truth if you ask the same question for a matrix of n by n cube, for example, we should say. But I don't know for n by n, and it's interesting. It's also interesting to find an explicit function. Here is another thing. Suppose you order the endpoints with respect to some other distance, let's say AP norm. So it looks that still the number of ordering should not be too big. And the proof I showed would work if P is rational with bounded in the numerator and denominator. Would be but what if P equals pi, for example? It still looks that probably you cannot get too many. And in fact, also it looks that in this theorem about the number of sign patterns of radicals, the dependence on the of the number of connected components, let's say, on this R, the number of terms, right? So if each function is a linear combination of R square roots of a quadratic polynomial, let's say, then it seems that the correct behavior there in this number of sign patterns should be better than what we get. And around here, this is something that I don't know much about, but it looks that this may be connected to what is called the O minimal theory. So it's talking Yokunov and Zakharov and Gal Binyamin and Pila. And it looks that it does not follow from known results, but maybe something that can be true. And finally, let me mention this, that for which configuration of point C in RD, or let's say in the plane, is it the case that you can get all permutations? Now you're allowed to use as many vantage points as you want. But I want to get all permutations. And still, it's not too difficult to show that not always you can get all permutations. For example, the points have to be in convex position. Something in convex hull of something else, and it's not difficult to see if you cannot get all the permutations. But this is not a necessarily insufficient condition, even in the plane. And using some nice, not so well-known result of Chamber, let's say, matrix, an n by n matrix, or in place ij, you write the Euclidean distance between point pi and point pj, where these are arbitrary points in the Euclidean space. This matrix is always non-singular. And you can use this to show that if C is symmetric, is transitive, so I wrote here, like the vertices of convex polygon, then it will be possible to get all the all the possible permutations, but you need quite a large number of points, so maybe some fractional power of n. And with this, so several people told me that they have to leave by 12, so it's a good place to stop, and thank you.